I'm Steve Whitaker. I'm the Principal Manager of Storage here at the Institute. And I'm part of the Institute's specialist team, so we work a lot with governments, industry, and a range of other stakeholders, basically around the world to try to accelerate demonstration of CCS technologies. And so one of these types of activities we do are host webinars such as this, and it allows us to reach a fairly broad audience. And in this case, we really do want to give a big welcome to everyone. I know we have people from quite a wide range of areas and countries around the world. And so I'm not sure if I should say good day or good evening or good morning. Basically, we're based here in Australia, so we're typically at a completely different time zone than the rest of the world at times. So a few housekeeping matters before we start. This webinar will be recorded and it will be made available on our website. So you'll be able to review this as you will, and also the slides will be made available also, and those will be up in the next few days. And one thing we'd like to point out is that questions are welcome throughout the presentation. So as you think of them, please jot them down and send them along. We'll go over the questions in a few minutes, but please post them as we go through the webinar. Questions will be moderated and posed towards the end of the presentation. So we'll discuss more about how we do the questions in a minute. So in the webinar today, we're going to discuss basin resource management, and there'll be an Australian perspective about this, but really I think this topic is broadly applicable. It's an emerging area. It's been a concept obviously that's been involved in all CCS projects to date. But the role of basin management is possibly becoming a little more prominent, and we'll discuss some of the stratigraphic and geomechanical aspects of CO2 injection and how it may impact the adjacent natural resources. So clearly most candidate CO2 reservoirs are in resource-rich basins that contain groundwater, oil, gas, unconventional gas, even geothermal resources, and other even natural gas storage facilities. So there's a tremendous diversity of resources that are in basins that may have some influence on your CCS project. So consideration of these things and designing these basin management procedures into your characterization activities is something that is very important. So this webinar is going to focus on what the current state of knowledge is in this area. It's been comparative analysis of existing resource use management systems, and it builds on some early workflows for assessing possible resource management, and it's going to provide us with a case study of the Southwest Hub in Western Australia. Now, if you're interested about this work, we also have on our website a complementary document that goes along with this, which is Basin Resource Management for Carbon Storage. And this report has been produced by CSIRO here in Australia and Curtin University. So as I mentioned, that is on our website, and you can just go to our publications and do a search for Basin Resource Management, and you'll find this document. So I'd like to talk a little bit about our speakers today. First is Jim Underschultz. So Jim is the General Manager of Research with ANLEC R&D. And before he took this role, he was really involved in a number of fairly high-profile positions here in Australia with CSIRO, CO2, CRC, and also before that in Canada at the Alberta Research Council. So Jim has a lot of experience characterizing fluid flow in the deep subsurface. He's had more than 25 years, 50 publications basically on fields of petroleum hydrogeology, basin analysis, seals analysis, and carbon storage. He's got a tremendously strong academic background. I've met Jim personally. He's got a PhD in membrane seal analysis from Curtin University in Perth, and a master's in geodynamics and a bachelor's of science in geology from the University of Alberta in Canada. And Jim's co-author in this is Sunil Varma, and Dr. Varma is the research team leader at CSIRO Earth Science and Resource Engineering, and he's also leading the Basin Resources Management for the Carbon Storage Project. He's got also a very broad experience in assessing the impacts of climate change and also the abstraction of groundwater resources in several basins in Australia. currently very much a key member of CSIRO's research program, and he's looking at the conflicting use of the basin's pore space due to the multiple use, such as petroleum and groundwater. So basically the topic of this presentation. So Sunil's background is with a PhD in applied geology from Curtin University in Perth, a master's in exploration geophysics, and a bachelor's in geoscience, geological science from the Indian Institute of Technology. So, as I mentioned, we will be taking questions throughout this session, and we will try to get through as many questions as we can. So I will encourage you to submit questions as they come to you using the Questions tab on your GoToWebinar control panel on the screen. So you should be able to come up with something like you see on the screen right now, and just type in your questions and send them as they come to you. And we will address these, as many as we can, at least at the end of the session. So with that, I think I'd like to hand over the presentation to Jim and Sunil, and they will go forward with this presentation on basin resource management.
Okay, thank you very much, Steve. It's Jim Underschultz talking here from ANLEC R&D. I'm assuming everybody can see my screen now. I've got the title slide up there, Basin Resource Management and Carbon Storage. And as ever with these type of projects, there's really a host of people that are responsible for a lot of the work and thought that's gone into what we'll be showing today. I'd just like to acknowledge some of those people and like to really thank the Global Institute for hosting this webinar. Some of the people involved early days actually were IEA, GHG, and Kathy Hill at the Global Institute. And then there's a lot of the work has really been put in by the Basin Resource Management Study Team here at CSIRO and Curtin University in Perth. And that involves people like Jane, Boskert, Laurent, Karsten at CSIRO, and Brett at Curtin University. And in addition to that, really we've had a lot of input from different institutions here in Australia, the CSIRO, the CO2 CRC, which is a really big research organization in carbon storage, carbon capture and storage here in Australia, ANLEC R&D, which is my host institution, the Global Center, and a number of the research sort of universities like Curtin University, and as well as the state surveys and the federal survey in Australia. So really there's been a lot of people with input to what you'll be seeing here today. Just like to make acknowledgements to our funders, which include ANLEC R&D, Australian Coal Association, and the federal government, as well as co-contributions from some of the research organizations such as CSIRO, Curtin University, and as well as the West Australian Department of Mines and Petroleum. So just a quick outline of what we'd like to present to you today is we sort of walk our way through, first of all, what are some of the main parameters that we consider when we're talking about carbon storage in the deep subsurface, why resource management issues are becoming sort of an important consideration in carbon storage, what types of resources we'll be considering here in the webinar today. We'll give an example from the Gibson Im Basin in Victoria here in Australia. The Gibson Im Basin is a great case where we've got really a lot of defined resource potential across the basin. So that's a great example of that. We'll be talking a bit about some of the major CCS projects that are either active or planned here in Australia. And then again, putting in context really issues of scale, both in terms of time, volume, rate, and geographic area, and how these things matter when considering resource management. And then we're going to end the webinar with a case study from the Southwest Hub in Western Australia and a few summaries and conclusions. So first of all, I just wanted to quickly highlight some of the really main components that we consider when looking at carbon storage projects. And this diagram really just highlights the three main ones. At the bottom here is injectivity, or our ability to get the CO2 into the reservoir rocks in the first place at the rates at which we'd like to. The second major area of investigation is capacity, storage capacity. Can the reservoir rocks in the zone of our interest have the capacity to store the volumes of CO2 that we would like to? And then the third component is containment. and that's really considering, in terms of doing carbon storage for climate mitigation purposes, we'd like to ensure that roughly 99% of the injected CO2 is contained over a 1,000-year time period. And then within those three major sort of areas of investigation, we need sort of to be able to measure things, and we need to be able to verify that what's happening is what we expected. And that's really the box around the outside here of the M and V. Some people have MM and V, which is measurement, monitoring, and verification. And that's discussing really what are the types of things that we need to do to be able to confirm that these three aspects are what we'd like them to be. So I guess the real question here that we'd like to try to answer is, why is resource management important in carbon storage? And of course, as we progress to larger and larger storage volumes, we're utilizing the pore space in sedimentary basins to keep or store CO2 and keep it out of the atmosphere for this sort of 1,000-year time period. And of course, within those sedimentary basins, there's other valuable resources that human beings can utilize. And we want to make sure, from a regulatory point of view, that we're managing those various resources and access to those resources in a responsible way. So the location and character of the resources can have a pretty strong impact on how we might try to characterize and understand our carbon storage project. And some of the things that might do is, first of all, influence the storage site location itself. So just first of all, having an understanding where the basin resources are could help you in your site selection process. And that really relates to issues on the right here of capacity and containment. The other thing it might do is impact our understanding of the dynamic storage capacity of the site. So I'll give you an example here would be, perhaps we've got an oil or gas reservoir that we've discovered, and we're draining that, and we'd like to produce that hydrocarbon over a 20-year period. However, that same sort of reservoir zone provides pore space that would be really useful for carbon storage. So we might design our carbon storage project such that we put the CO2 in along a migration route that eventually leads towards that hydrocarbon resource, and plan it in such a way is that we've been able to utilize the hydrocarbon resource and drain those resources by the time the CO2 migrates and arrives, and eventually ultimately uses the pore space where the hydrocarbons were before. So we can think of storage capacity in kind of a dynamic sort of concept where over time our storage capacity number might change. The other thing it might do in terms of understanding basin resources is guide our containment risk assessment. So really the thinking here is that if we've got a carbon storage project and we need to put in place a few monitoring and verification strategies, either remotely or through well-based type strategies, we might focus that sort of monitoring around existing resources, other resources that are occurring in the basin. So we can go back to the previous example. We might have a pressure monitoring bore partway between our injection site and that depleting hydrocarbon field so that we can keep track of the progress of that CO2 storage in relation to the depletion of that field. Finally, understanding of the resource management could help us in terms of that monitoring and verification design. So how we actually even look at building that sort of monitoring verification system. So what I'd like to do next is talk about the Australian context, which in some ways could be a little bit different from some other areas of the world where there's some pretty high-profile carbon storage projects. In Australia, first of all, we're a very dry country, has a lack of surface freshwater resources, and as a result, there's a sort of a premium placed on our groundwater resources, really important to Australian society. It's relatively deep groundwater resources in Australia compared to lots of other places. There's locations where you can get well below 1 kilometre depth and have still potable groundwater resources. The Great Artesian Basin is one example of where we've got deep groundwater resources. So this can be quite different than a lot of other areas where you might be looking at carbon storage projects elsewhere in the world. An interesting thing about our oil and gas resources is that they're often largely located within a single reservoir horizon. For example, the Gibson Im Basin that we'll be talking about today as an example has by and large, the bulk of the conventional hydrocarbon resources are from within one reservoir unit, the Latrobe Formation. This is partly due to the fact that Australia's basins tend to be a bit underexplored compared to places in North America or the North Sea, for example. But it's also a function of our geology. That can have important implications in terms of basin resource management here in Australia. Much of the Australian geothermal energy potential is in hot sedimentary rocks. So it's a fairly stable sort of cratonic area where we don't have a lot of volcanic rocks. So in terms of understanding the geothermal energy, it tends to be hot sedimentary rocks. Australia also has large coal and coal seam methane resources that we need to consider. There's no shale gas production yet at this stage, but there's certainly an evaluation going on as to what our shale gas potential is, and that's certainly something that we want to try to understand from a resource management point of view. So the next question is just what resources are we going to be interested in, what will we be talking about today? So I'm going to use the sort of Gibson Im Basin as an example here, but first I'll sort of walk you through this map. This is a fantastic map produced by the CO2 CRC. That's a guide to some of the major CCS projects in Australia. Now, just to get your eye into this, on the left-hand side in the sort of the legend here, the blue, dark blue symbols are the capture projects, and the type of symbol relates to the sort of stage at which those projects are. The red symbols are for storage projects, and again, the type of symbol relates to the stage those projects are at. The light blue circles are major point source emissions of CO2 in Australia. The green sort of little star are places where the federal government has issued carbon storage permits. Those are in offshore waters. And finally, the main sedimentary basins are indicated in these shades of sort of brown or salmon color. Now, in terms of storage projects, I just want to point out 4 or 5 major projects. The first one is the CO2 CRC Otway project in Victoria here in the southeast. That is Australia's only active carbon storage project, and that's kind of at a pilot scale research facility in the Otway Basin of Victoria. Another big project that's going to be coming on stream that many people will have heard about is Gorgon in the northwest shelf of Australia. This is a commercial-driven oil and gas project associated with CO2 from a large gas field, an LNG facility, and there'll be a carbon storage project in the northwest shelf of Australia at Gorgon. Then the other 3 major projects really are Australia's flagship demonstration projects. There's 3 of them. There's one in the southwest hub of Australia here in the western part of Australia near Perth. In Queensland, there's the Wandoan project in the Surat Basin. And in Victoria, there's the CarbonNet project that's in the Gibson Im Basin. These 3 flagship projects are really at the site evaluation stage of those projects, where they're sort of proving up the storage potential and containment security of those areas. So what I'm going to do is just talk a little bit about the Gibson Im Basin. The Gibson Im Basin and its resources sits over on the eastern coast of Australia in Victoria here in the yellow circle. So I'll walk you through some of the permits in this region. I've zoomed in now to the Gibson Im Basin. The blue is the offshore areas. All these sort of dots on here are the exploration wells that have been drilled. The green ones are where there's oil discoveries or production. The red ones are gas discoveries, and the black ones are dry holes. So you can see the basin extends in an onshore area as well as an offshore area of the Gibson Im Basin here in southern Australia. So this first diagram is just the oil and gas production permits. So these are areas where there's discovered hydrocarbons that are under production and at various stages of depletion. Some of the fields in the offshore here, the oil fields, are getting fairly depleted. Some of them have up to well over 90% water cut, and they have very, very high primary recovery. So utilization of CO2 from an enhanced recovery point of view isn't a very big option here in Australia. These are the exploration permits in yellow for conventional oil and gas in the Gibson Basin, some on the onshore and quite a few large areas in the offshore. These are areas are located here in purple, and these are future areas that could be released for exploration. And finally, the retention licenses are places where there's companies who've got an interest and they're retaining those licenses for future development. Geothermal permits are in the onshore area. That's these pink areas, very large permits, and I think there's only about 4 here indicated, but those are in the onshore area. So those are places where there's potential for geothermal resources. And there's a sequestration permit in the offshore that's been put out by the federal government, GIP 001 in green. So if we put all those things together, it gives you an idea of what the potential range of resources are and their distribution. And just keeping in mind on the bottom left-hand corner, there's a scale bar of 0 to 50 kilometers to get you in the right space scale. So already you can kind of see where we've got juxtaposition of a number of different sort of geothermal, carbon storage, and oil and gas, conventional oil and gas. And so far we haven't even talked about sort of coal resources and other things like that in the onshore area. So how do these interact with water resources? Now this is roughly the same area, slightly different geometry of map. I'll get your eye into it again. This dark black line through here is the coast, so onshore to the left, offshore to the right. The dashed orange line is the basin edge of the Gibson Im Basin, so that's the pinch out. And we've got a few in the red dashed lines, the major basin-forming fault zones. Now this is, the contours on this map are from a sort of a public open file report of CSRO in 2004, characterizing the hydraulic head within the Latrobe Aquifer in the Gibson Im Basin. And this hydraulic head distribution represents roughly the mid-1990s. And this is after a fair bit of production has happened in the offshore from oil and gas. And you see this, basically what it's showing is the pressure drawdown within the Latrobe Aquifer associated with hydrocarbon production, primarily from the oil fields. This work, I just sort of point out, has been under continual update, and there's lots more information out there. This is just a very convenient one to refer to in terms of being in the public domain. So there's certainly been a lot more work on this since the publication of this map. So the thing to point out is that within the Latrobe Aquifer itself, obviously the hydrocarbon production itself is having an impact in terms of the pressure drawdown on that system. As well, onshore, we've got large brown coal deposits and open pit coal mines. They dewater the Latrobe Aquifer to get the water table below the base of the mine to keep the mine stable. And that produces a drawdown cone here in the onshore regions of the Latrobe. That also is causing an impact on the groundwater resources within the Latrobe Formation. And finally, there's an awful lot of agriculture occurring along this region as well. And it's been sort of drought conditions over a number of years in Australia, and the agriculture industry is relying more and more on groundwater. And some of that groundwater in the onshore areas, the Latrobe Aquifer, it actually is usable for agricultural purposes. And there's local drawdown cones from irrigation, production for irrigation. So you can see that there's a number of places that are, depending on what the resource is having some impact on groundwater resources. I should point out that this is the Latrobe Aquifer system we're mapping out. If you come to shallower aquifers, you go through the top seal for the Latrobe, and the shallow aquifers aren't affected basically at all by any of these drawdowns. These are just within the Latrobe system. So within that, there's a couple of places where there's potential for carbon storage. In the offshore, I showed you that GIP 001 license, and these are places where they're looking. So of course, if we're using the Latrobe to store CO2, that's going to be increasing the pressure in some of these areas rather than decreasing from some of the other production type activities. So these are some of the things that we'd like to consider in terms of an overall basin management of the various resources and their impact on the water resources. So one of the interesting questions that we also need to ask, and certainly from a regulator point of view, is that not only do we want to consider what the current known hydrocarbon resources are, or other resources, but what about the undiscovered potential? And this gets to be a little bit more esoteric, I guess, and certainly more uncertainty in that, but it's still a question that is worth asking when considering where in the basin you might want to use for carbon storage. So some of the questions we might ask ourselves in this sort of realm, and this is really the places that do this job the best are the National Geological Surveys. The USGS has a fantastic system of evaluating undiscovered hydrocarbon potential, and I'll rely on that a fair bit to sort of highlight this. So some of the questions we ask ourselves is the basin more than 2 kilometers thick? And this is really related to if it's got the potential to get the kerogen into a place where it can be converted to petroleum. Is there a demonstrable hydrocarbon system already evident in the basin? Are there reservoir seal pairs? What are the critical moments in the basin history so that we need a sort of a confluence of timing of hydrocarbon generation, migration, and trap formation? So if you generated your hydrocarbons and they all migrated before the trap formed, you don't trap any hydrocarbons. So you need really all these components to be operating in sync to produce a hydrocarbon system that leads to resources. What are the characteristics of the existing hydrocarbon discoveries? And are there hydrocarbon shows or indicators in the area of interest? So I'll just give you a little example again from the Gibson Im Basin, and this is work done by the USGS. And this map here is basically across the top is geological time coming from the present day on the right through to sort of into the Jurassic on the left-hand side. And then down the vertical column here is it's a series of the key components of a hydrocarbon system. And where they're flagged in geological time is the point at which those rocks, in this case source rocks, were deposited. We had reservoir rocks in the next layer down being deposited in the blue bars. Then the seal rocks were deposited over these geological periods of time. Finally, the overburden rock, which allowed the sort of the basin to subside and go through the oil window to produce the hydrocarbons, were deposited here. Trap formation, and this is really where we're doing deformation to the basin that allows us to form structures that will trap hydrocarbons, occur at a couple of points in time in the basin history. So then we've got a combination of generation, migration, and accumulation occurring here with preservation in the last period of time. So we can look at this entire history and come up with a critical point in the basin's history where we had all the components of the hydrocarbon system and trapping system required to be able to make this into a sort of a resource-rich basin. And you can do this type of analysis for basins, even in a situation where there's basically no hydrocarbon sort of, or no exploration wells been drilled yet. And this gives you some idea of the resource potential for that basin. There's another way to look at undiscovered hydrocarbon potential. And again, here's an example from the USGS. And this is just looking at the existing distribution of hydrocarbons that have been discovered. And you can look at a basin and see what are the characteristics of the hydrocarbons that have been discovered, and based on that distribution, you can make an estimate of the undiscovered hydrocarbon potential. And that's a fair bit of work, again, from the USGS has gone into these processes of trying to evaluate hydrocarbon potential. So that's just another approach that you can take. This next diagram is another sort of diagram to get you thinking about things we need to consider in terms of resource management. I did not mean this to be an example of the Gibson Im Basin. This is just an extremely sort of generic case to show it's not necessarily just the physical interaction of the CO2 with the other resource that you might be considering, but it could be implications because of pressure distribution, not necessarily the CO2 itself. So what I've got is on the top here just a little example where we've got a shallow aquifer system in light yellow at the top, when you can see that's going into an offshore area. We've got a seal horizon in red, and below we've got some deeper reservoir unit that has got formation water there, but we might consider putting CO2 in that for storage. So the top diagram would be the pre-injection flow system, where we've got recharge in the high topography, gravity-driven flow system, then we horizontal flow through the surficial aquifer, as well as down in the deeper sort of aquifer. And we've got a certain amount of leakage occurring vertically across that red aquitard. And the rate of that leakage would be totally dependent on what the permeability of that red seal rock would be. The diagram on the bottom would be an example where we used a series of injection wells and stored some CO2 down in that lower grain unit and increased the formation pressure in that location. Now, by virtue of doing that, we could be 100% secure of CO2 itself being contained below that red seal, although because we've increased the pressure, it increases the hydraulic gradient across the seal, and therefore it also increases the flux. So in this zone through here, we could have a situation where there's a certain amount of leakage of pore fluid that was originally within this red zone that is now coming out into the aquifer above. So the question really that we need to think about is, if the pore fluid in the red zone is perhaps higher salinity than what's in the shallow aquifer, is that going to have an impact or degrade the quality of water in the shallow aquifer? There's a number of people that have looked at this issue in different places of the world. One in particular has been in Texas, in the Gulf. And by and large, when you model these things and look at it, the answer that comes out tends to be a pretty insignificant amount. However, it's still something you need to look at because, of course, the details depend on the specifics of your particular spot you're looking at. And in this case, the flux is really strongly dependent on the permeability of this red seal zone. But it's still something we want to look at and be able to tick that box. So I just get to the point here about scale. And everything that we talk about in this webinar really is, we need to think about it in the context of the scale. Scale of volume. So, for example, if you're doing a pilot test of 100,000 tons of CO2 storage, that's a completely different sort of question in terms of resource management than if you're doing 3 million tons a year from a small power station. Rates as well makes a big difference, of course, in terms of pressure in the subsurface, or the rate at which you'd like to put the CO2 in the ground, the geographic area that's impacted, and the length of time that you're considering. Are you considering just a 30-year injection period, or are you considering 1,000 years over which you'd like to keep the CO2 stored? So in all of these things, it's really important to put it in the proper context of scale. So that gets us through to the point where I'd like to talk about a case study example. I'm going to use the southwest hub of Australia here in the western side of Australia, where I'm going to just walk you through the process and the workflows that we've been using to evaluate the resource potential of the region, where we're looking at the possibility of a carbon storage project and where we're at with that. So just to get your eye into it, here in the top left is a map of Western Australia. The little red box here down in the sort of southwest corner is our area of interest, and that's blown up here in the sort of the yellow map. On the right-hand side is a photograph of the GSWA Harvey 1 data well. That's just been drilled, and that's our first sort of stratigraphic well to get information to start to characterize this zone to see how it's going to potentially behave in terms of a carbon storage project. That well was sort of drilled in February and early March this year, and we're literally in the process of we've recovered an awful lot of core and run logs and things like that from that well, and we're really in the process now of evaluating that information and updating our models. The well got down to roughly 3 kilometers deep. So a couple of the points here is that we've got an initial 2D seismic grid that was run in these dark green lines, and that was run on existing along roads that occurred through that study area. And then along near one of those lines, that's the location of our GSW1 Harvey well, so that we can tie the information from the well to one of the seismic lines. And then we're going to go through to the next stage of doing a 3D seismic and potentially a site selection and further characterization with new wells to come. So we're still fairly early in the process of trying to evaluate the potential for this site. Here's just a cross-section, the location map on the right-hand side. It's a north-south cross-section. Onshore is in yellow, offshore is in light blue, and it highlights through the region of interest the main structural feature through this area, this anticline shape, basement high called the Harvey Ridge. And the really thing to point out here, the reason why this area was of interest is because exactly related to resource management. What you'll see in blue here, Yargadee Formation, and in Western Australia in the Perth Basin, the Yargadee Formation forms a major freshwater aquifer system that's used for various industrial and human consumption. And you'll see to the north, up in this part of the cross-section, we've got this wedge of Yargadee Formation and the development of this major freshwater aquifer. And again to the south, as we get further south from Geraldton, it comes back in. But across the Harvey Ridge, there's this angular unconformity, and by and large, that Yargadee Formation is absent. So all we're left with in this area is a very shallow, superficial groundwater sort of system, and this major freshwater resource is absent in the region. So not only does this structure provide us an interesting sort of trapping mechanism and a zone in which we might store some CO2 somewhere down in this location, but also it's in an area where we're avoiding any potential interaction with this major freshwater groundwater resource. So what I'm going to talk about in terms of the Southwest Hub is groundwater, hydrocarbons, coal and coal seam gas, and geothermal, but that in itself isn't quite enough. We need to put that in the context of a structural, stratigraphic, and geomechanical evaluation to assess the containment security and the likely interaction of these different resources with a carbon storage region. Now, a lot of this sort of assessment of the containment security is currently underway. I sort of flagged the fact that we've just got this first data well, and of course we've got logs and core and lots of information from that data well that's now feeding back a whole series of projects that are utilizing that information to update our understanding of the area. So some of the things that we're looking at: seal thickness and permeability, that is underway, so that's really understanding the top seal capacity. Related to that is the in situ stress and the horizontal stress anisotropy, and it turns out that in this region there's quite a strong horizontal anisotropy, and of course understanding the stress and the geomechanics of the top seal gives you an idea of the rock strength. We've done a leak-off test in that well, and in this case the seal rock strength is really quite high. We couldn't achieve leak-off actually. And then so that sort of takes care of the top seal analysis that we're working on. And then there's a series of things that we're interested in terms of the fault zones in the region. The first is just the fault zone architecture, and that includes things like the throw distribution, the orientation, and the detailed geometry of the faults and the offset sort of splay type faults. And that architecture, in the context of the in situ stress field, gives us an idea of what the upfault leakage potential is or not, and things like juxtaposition across the fault in terms of cross-fault leakage. So that analysis is currently underway. The other thing that we look at is fault zone membrane seal capacity, and this is really the cross-fault leakage potential from a sort of capillary type of analysis, and that's looking at shale gouge ratio or some equivalent to that, and what the permeability likely of that fault zone, of each fault zone likely is. There's also fault reactivation potential or fault strength, and again that relates both the sort of the architecture of the fault together with the in situ stress gives us some idea of what the reactivation potential of those faults are. And finally, we've got the potential for leakage from wells, existing wells. In this case, there's not very many wells in the region. So those are some of the things that are currently underway. So the next slide shows the groundwater in this superficial aquifer system. The map here on the left again is the region, sort of quite a large region of southern part of the Perth Basin. The ocean is in white, and the onshore area here is in yellow. The detailed area of interest for carbon storage is outlined here in this yellow box. And we can see that the flow systems in this are really from the high topography along the Darling Scarp here, high topography on the east, driving a gravity-driven flow system towards the west into the offshore. This next map I'm going to describe again. Here's that same geographic area on the left-hand side with our detailed area of interest, and now the contours on this are the salinity of the formation water in that surficial aquifer. So in this region, I've just flagged off now in blue the zones that are less than 1,000 milligrams per liter salinity. What I'll focus you on now is this cross-section through here on the red line, and that's a series, another little inset map here on the far right, a series of very deep groundwater monitoring bores called the Binning Up Line that runs east-west from the Darling Fault Scarp through to the offshore area. And the zone in the middle here is the cross-section along that red line, and we can see this sort of running through here, indeed the freshwater zone of that superficial aquifer of less than 1,000 parts per million or milligrams per liter. And the key point here is that if you look at the vertical axis here, really you only have to get 100 or 200 meters deep, and already you're moving into zones of about 20,000 parts per million or so salinity. So in this location, really, we don't have this deep groundwater resource. It's really just the superficial resource. Here's another view of that same area with our area of interest in yellow. And the map on the right shows the water allocation regions defined by the Department of Water. And on the left, we have a series of dots which are really representing the extraction, current extraction from the Leaderville, that's superficial aquifer. And you'll see to the north, there's quite a lot of use of the aquifer as we get further to the north, away from the Harvey Ridge. And again, to the south as we get further away. In the zone of interest, really, the water quality deteriorates and it's very thin, so there's not a lot of use of shallow groundwater resources in that region. Now the oil and gas permits, this is the area of interest. There's our carbon storage study area of interest, and we see that there's various hydrocarbon exploration permits been issued. There's offshore sequestration permits here in green, and again, these are, in Australia, the offshore is controlled by the federal government, the onshore is controlled by the state government. So because so far the federal government has issued sequestration permits, all of the current sequestration permits are offshore. The WA state is in the process of doing something similar for the onshore, and they'll undoubtedly be something should this area prove up to be of interest. Here's the geothermal permits in the onshore area. So again, if we put everything together, we see that we've got still a number of interesting resource potentials in the region that we're interested in, that we need to be cognizant of. So what I'd like to do now is just look at a few of the coal resources of the region and see how that resource potential stacks up relative to the area of interest for carbon storage. Now, I'll discuss this a little bit. I'm going to do this through a whole series of these different types of coal resources, and what it is on this vertical axis is depth, and then these blue bars in this case are examples in terms of coal mining, the depths at which there's commercial coal mines internationally, these kind of surface type mines, and the red ones are examples within Australia. And we can see that basically there's some economic limit at which point it's infeasible really to be getting coal from a mining sort of potential with depth. And it tends to be cut off internationally about 1,500. In Australia, it's even shallower than that. In the region here of interest, we've got shallow coals in the Catamara coal measures between about 100 and 2,400 meters. They've not been very well defined, but we've got our new data well in the region that's helping that out. And basically, these things are looking to be pretty immature coals and very thinly sort of bedded and horizontally discontinuous. So the economic potential of these Catamara coal measures in the region appear to be pretty low. And as we sort of process the information from our data well and collect more seismic and so on, we'll put more information to that. But at this point in time, the resource potential really looks pretty low in terms of those coals. Deeper, we've got the Sewell coal measures, which are higher grade coals and much more interesting, but they occur deeper than 3,000 meters in the area of interest. The zone at which we're looking for carbon sort of storage in this region is really between 2,000 to 3,000 meters, more or less. So we're quite nicely in a zone where we're probably not going to have much conflict with any coal mining sort of potential in the region. It's either too deep, such as the Sioux coal measures, or the stuff in the shallower zone just is sort of sub-economic. If we look at coal seam gas potential related to coals, again, internationally we can see the depths at which coal seam gas is utilized. In the US, down to about 1,200 meters. In Australia, the red bars here, about 800 meters is the deepest production so far, but there's estimates that we could get down below 1,000 meters with some of the new potential in Queensland, in the Latrobe Basin, for example. So if we think about that really relative to the carbon storage potential, again, we're sort of in a zone below 2,000 meters, which is well below this zone here. The shallow coals in our region tend to be these discontinuous, thin, low-grade coals, so they don't have much coal seam gas potential anyway. The Sewell coal measure might, except it's down at 3,000 meters. So again, the geometry and the geology here would suggest that in terms of coal seam gas, there's not really much resource potential in this particular region. Another way of utilizing coal is underground coal gasification. There's a number of projects internationally at depths down to about 1,400 meters. There's an example of one project in Queensland that's sort of at about 300 meters depth, and there's potential anywhere down to 1,400 meters as well in Queensland in the Surficial Basin. And again, we can compare that to our carbon storage potential, which is down to below 2,000 meters. Again, we have to remember that in this region, the shallow coals really are this low quality and discontinuous seams, and the really interesting coal from that point of view is below 3,000 meters, which is well below the economic depth in this region. So again, in terms of the coal resources, there's not much in terms of identifiable usable resources in this region. In terms of oil and gas potential, we can think of both conventional oil and gas as well as unconventional. And I sort of flagged in a previous example of where those permits were located. In terms of discoveries, there's our area of interest in terms of the carbon storage sitting on top of that Harvey Ridge in the onshore area. There's some discovery of about 7.5 meter oil column here at this well in the offshore to the north in the area. And again, to the south of the area, there's some reserves associated with the Witcher Range field. These are in deeper Permian strata, and it's a tight gas resource down to the south. In terms of geothermal energy potential, I'm showing on the left-hand side all the temperature data from the Perth Basin, increasing depth on the left-hand scale, increasing temperature on the right. It's the exact same data on the right, except I put some interpretation on the top. So the yellow lines are really the total range of possible geothermal gradient through the South Perth Basin. There's a nearby well, Pinjarra 1, that we modeled what we thought was the probable temperature profile in the red line, with an uncertainty here of that model in the green bars. And it turns out our new data point from the Harvey 1 well is sitting at this location here. And that gives us a geothermal gradient of about 20 degrees C per kilometer, which is pretty low in terms of a geothermal energy potential. Average gradients are quite often up to about 30, generally speaking. So this is pretty low geothermal gradient in this region. So again, in this particular area, the geothermal energy potential is pretty minimal. It's hard enough to make hot sedimentary aquifers work in the best of cases. If you're down around a 20 degrees C per kilometer, it tends not to work very well at those reservoir depths. So in summary for the Southwest Hub case study, the geomechanics of the top and fault seal evaluation are underway, and we're utilizing the data from that new data well to understand the containment risk analysis. Groundwater management issues in this region are minimized because of the absence of the ERGD aquifer. We've really got just that shallow surficial aquifer to consider. The Leaderville aquifer, and that's what I just mentioned, is the superficial aquifer is shallow, and that's the one we really need to think about in terms of a resource. In terms of coal and coal seam gas resources, really it's minimal resource potential because the shallow coals are really low grade, and the good quality or the better quality coals are deeper than 3,000 meters, which make them pretty much sub-economic. In terms of conventional hydrocarbon potential in this region, it tends to be low. There is some tight gas potential in that Gillespie formation at depths below 3,000 meters that needs to be considered. And in terms of the near surface temperatures and the geothermal gradients, these are generally not suitable for geothermal energy development in the area. So the approach taken here is to really try to understand, first of all, where the resources are and what their quality are, and that all fed into really helping us understand this case. So what's next for the Southwest Hub? We've got continued sort of detailed site characterization with our new data well. We'll update the various models. We'll look at dynamic multi-phase reservoir simulation and updating that in terms of understanding what the CO2 might do in the reservoir unit. We're going to link both the reservoir model with the shallow groundwater models to try to understand potential interactions, and what I talked about earlier is that vertical leakage potential. A little bit characterize that a little bit better. And I guess the final takeaway here is that this kind of approach is pretty transferable to other regions that you might want to look at in terms of carbon storage. So with that, I'd just like to sort of thank my co-author, Sunil Varma. I really appreciate your time, taking time out to listen to this webinar, and thank the Global Institute for hosting it. I hope that was useful for people and give you a bit of an idea for those of you international some of the projects that we're working on here in Australia and some of our approach. So I think at that point, I might turn it back over to Steve in case there's some questions that might have come up.
Well, thanks very much, Jim and Sunil. That was an excellent presentation. I think the examples of using water, drinking water as a resource, and also coal as some kind of tangible, extractable fossil fuel type of resource, and then also using the potential for geothermal energy was really a great spectrum of resources that showed to be possible interaction. So I appreciate that very much. We do have a few questions that I'd like to get at. I'm going to take the prerogative of being the MC to ask the first one, though. And I see all these other resource industries doing their activities, and a pretty good example is in the Gibson Im Basin area. The oil industry is extracting water, and the coal industry is influencing the hydrogeology there. It seems like the basin management planning is falling on the shoulders of CCS projects. Do you see other operators having to do the same level of basin management for protection of resources? Do you see this maybe in the future becoming more of a cooperative activity among different players in the field?
Yeah, Steve, can you hear me there?
I certainly can.
Okay, thanks for that, Steve. Look, I think one of the things we've certainly been involved with here over the years, previously with CSRO, and I know CSRO is currently today, working with state and federal government in terms of understanding what those resource interactions might be. Certainly the Gibson Basin has been one example where because the main zone of hydrocarbon production and the main zone where the onshore coal is located also has some water resources potential within that reservoir itself, is one of the areas that has had some attention certainly in Australia over the last, I'd say since sort of early 2000, for exactly that reason. And probably that location is one of the first areas where this has become really something that has piqued people's interests. And that's because the Gibson Basin is one of Australia's premier conventional hydrocarbon resource areas, and it's been producing for 30 years. Having said that, it's still reasonably underexplored if you compare the basin to places like, the Western Canada Sedimentary Basin or the Gulf Coast or the North Sea. So in a sense, I think the Australian state and federal regulators are sort of getting onto this topic of trying to understand basin management reasonably early on in the basin development compared to lots of other areas of the world, and it's certainly an active area of sort of research.
Well, can I ask an answer, Jim? As a part of our project, we are developing a guideline document that will assist operators and regulators understand what steps that need to be followed in order to make a proper assessment of, characterize the different resources there and make an assessment of potential interactions. So that document will be very helpful when it's completed.
Yeah, okay. Well, thank you for that. I think in the interest of time, we'll go to some of the questions submitted by some of our listeners, and I encourage anybody out there to please submit questions, because we will send these questions on to our speakers even if we don't get at them today, so please don't hesitate. So we have a question from Warwick Stapleton, and his question is that he's heard that after Japan's Fukushima incident, the country is progressing hydrogen sourcing very quickly, including from brown coal in the Latrobe Valley. Of course, this will require some CCS. Is there any update on storage moving to commercial to enable hydrogen export? So I'm not sure if you can comment on that or not, but if you can.
Sure. Look, I think what I can comment on is, I guess, the state of how Australia is moving towards commercial scale carbon storage. And one of the maps that I showed in part of the presentation really highlighted 4 major projects in Australia. One is associated with oil and gas development on the Northwest Shelf with the Chevron's Gorgon project. And that project is really significantly advanced and will be in a position for, I believe, first gas is predicted in late 2014, early 2015. And then the other 3 projects that are really quite active are the 3 flagship projects with really projection to have pilot scale injections in about the 2015 timeframe, and should those move forward and prove successful, prove up this commercial viability with storage more towards the 2020 timeframe. So I think certainly that we're moving along the track. One of the things that you'll notice internationally, I guess, is that most of the commercial projects have got a U in the CCS, which is utilization, and that tends to be associated with things such as enhanced oil recovery. There's also some interesting links between carbon storage and geothermal potential using the CO2 as the working fluid. So there's people looking at a number of different aspects there from a utilization point of view. We tend not to have the opportunity quite so much here in Australia for enhanced recovery options. First of all, because we tend to be a gas-rich region, but secondly, because our oil, where we do have oil, the oil is very, very high primary recovery. So really, Australia is perhaps a little bit behind some of international, like United States, or some areas of Europe that are using this utilization component. But I think in terms of the sort of the real storage component, we're reasonably on track there.
Well, one of the questions that popped in my mind when you were talking there has been raised by one of our listeners as well. So Matthias Rab has asked, have regulators for the Gibson Basin flagged expectations for project proponents, such as CarbonNet, to evaluate impacts on basin scales?
Yeah, I'm not. I don't think I'm in a position to offer comment on how the regulation is going to, what the regulatory requirements are going to be on individual proponents. I'm really not sure I can answer that one.
Okay. Well, we have a question from Jose Condor, and I know Jose, so hello there, Jose. Have you considered the case of 1, joint pore space utilization, and 2, stacking of reservoirs?
Okay, joint pore space utilization. I guess the 2 examples that I could think about there is the first example. One of the things that we've been looking at here in Australia is this concept of sort of transient, I guess it's the dynamic storage capacity. So we've got an awful lot of hydrocarbon reservoirs that are under production, and in sort of 20 years or 30 years time are going to be depleted. But we don't necessarily want to wait for 20 or 30 years to be able to start carbon storage, and we'd like to ultimately use that depleted pore space from the hydrocarbon production as an ultimate source or sink for the CO2. So one of the things we're really looking at is understanding the hydrocarbon migration systems very well for those hydrocarbon systems, so that you can go down dip on that migration system, use that for the injection of CO2, have the CO2 migrate along the hydrocarbon migration system, take up residual trapping potential, dissolution trapping potential, and eventually show up at the depleted field at a point at which you're finished with the field, and have the security of that known sort of trapping potential of the depleted field as the ultimate destination of the injected CO2. So that's certainly, I guess, you might consider that as a dual use mechanism. One of the other things that I mentioned might be considered a dual use mechanism of pore space is utilizing the stored CO2 as a working fluid for geothermal energy. We've got a combined project between Australia and Lawrence Berkeley National Labs associated with the CCARB project in Mississippi, where there's an existing carbon storage facility there. They've already sort of saturated the reservoir, and the temperature is such that we're going to do a little pilot test to see if we can then circulate the CO2 and run a geothermal power plant that will offset the compression costs of the CO2 injection. And that's really, I guess, might be another example of where you could consider it to be dual use of the pore space.
Okay, we have a couple more questions, and we'll try to get through, and then we'll probably be running out of time. So we'll just wrap up with a question from Seiji Hongo, and his question is really about how does mobility of CO2 injected into the reservoir really influence your planning or resource management?
Sure. So I guess one of the big considerations of understanding resource management is what the dynamic distribution of the CO2 is going to be over some given time period, and that could be, up to that sort of 1,000 years containment time period is what we might consider. So obviously, the mobility of the CO2 is going to depend on a combination of the permeability or the transmissivity of your reservoir unit and the dip, which is related to, the buoyancy drive. So certainly, dynamic reservoir modeling is an important component of understanding where the physical distribution of the CO2 might be over a given period of time. But I think the key thing is that in itself isn't enough, because particularly when you go to commercial volumes, it's not just the presence of the CO2 itself, but the distribution of the delta pressure or the change in pressure that could have important implication on other basin resources. So it's a combination of those two things. You want to understand the CO2 distribution, and its mobility is certainly a component, but also what the influence is on the reservoir pressure and the radius of that influence within the horizon itself.
Okay, we'll have a final question, and it's from Kelly Payne. If the Southwest Hub testing comes back positive, what sort of time frame would we be looking at before work commences?
Look, I think for the Southwest Hub, really the idea is to go through a series of progressions of investigation to test the storage potential for that region. So where we're at right now is we've got the initial data well to try to understand the geology. We've got a lot of core from that data well, and we've got well logs and things like that. So probably for the next year, basically, there's going to be analysis of that linked in with the existing 2D seismic program. Should the analysis of that work prove up that the storage potential still looks and containment security still looks pretty good for that region, the next stage would be to get a 3D seismic acquisition to really enhance, and what that's going to do is that's going to give us better predictability across a geographic area of interest. So then that will be a whole series of evaluating that relative to what we know from the existing well data. Should it still prove interesting, then probably from that we'd look at drilling another data well that we could do, perhaps some way of evaluating the injectivity of a zone of interest. So I suppose if everything proved to be very positive at every step of the way as we moved along, we might consider somewhere out around 2015 or something like that doing a small test injection of CO2 should that prove feasible. And at that stage what you can do is with a very small test injection you can evaluate the more commercial viability of that, and that's really up to that 2020 kind of time frame before you might be in a position to think about that.
Okay, well, thank you, Jim and Sunil. I'm sorry we couldn't get through all the questions, but please send your questions on. You can send them to the webinar at globalccsinstitute.com, and we'll have Jim and Sunil look at them and get back to you. And I just want to remind you that the webinar has been recorded and will be available on the website in the next few days along with the presentation. And also that a copy of the Basin Resource Management for Carbon Storage report is also available on the website for download. And if you have any difficulties with any of those, just send us a note and email that to the Institute email address. So I just want to thank both Jim and Sunil once again. It's good to have such expertise available to us, and I hope that you all found this webinar fairly valuable. And if you do, we sure like to hear any feedback on whether you find these useful or how we may improve our services. So thanks very much for attending this, and we'll see you at our next webinar. Goodbye.